What are gravitational waves? Let's maybe start from the basics.
We learned gravity from Newton, right? When you were young, you were told that if you jumped up, the earth pulled you down. And when the apple falls out of the tree, the earth pulls it down. And maybe you even asked your teacher why, but most of us accepted that. That was Newton's picture, the apple falling out of the tree. But Newton's theory never told you why the apple was attracted to the earth. That was missing in Newton's theory. Newton's theory also, Newton recognized at least one of the two problems I'll tell you. One of them is, there's more than those, but one is, why does the earth, what's the mechanism by which the earth pulls the apple or holds the moon when it goes around, whatever it is? That's not explained by Newton, even though he has the most successful theory of physics ever. Went 200 and some years with nobody ever seeing a violation.
But he accurately describes the movement of an object falling down to Earth, but he's not answering why that, what's the, because it's a distance,
He
right?
gives a formula,
right,
which it's a product of the Earth's mass, the apple's mass, inversely proportional to the square of the distance between, and then the strength he called capital G, the strength he couldn't determine, but it was determined 100 years later. But no one ever saw a violation of this until a possible violation, which Einstein fixed, which was very small, that has to do with Mercury going around the sun, the orbit being slightly wrong if you calculate it by Newton's theory. But so, like most theories then in physics, you can have a wonderful one like Newton's theory. It isn't wrong, but you have to have an improvement on it to answer things that it can't answer. And in this case, Einstein's theory is the next step. We don't know if it's anything like a final theory or even the only way to formulate it either. But he formulated this theory, which he released in 1915. He took 10 years to develop it, even though in 1905 he solved 3 or 4 of the most important problems in physics in a matter of months. And then he spent 10 years on this problem before he let it out. And this is called general relativity. It's a new theory of gravity. 1915. In 1916, Einstein wrote a little paper where he did not do some fancy derivation. Instead, he did what I would call it, used his intuition, which he was very good at too. And that is, he noticed that if he wrote the formulas for general relativity in a particular way, they looked a lot like the formulas for electricity and magnetism. Being Einstein, he then took the leap that electricity and magnetism, we discovered only 20 years before that, in the 1880s, have waves. Of course, that's light and electromagnetic rays, radio waves, everything else. So he said if the formulas look similar, then gravity probably has waves too.
That's such a big leap, by the way. I mean, maybe you can correct me, but that just seems... So that seems like a heck of a leap.
Yeah, and it was considered to be a heck of a leap. So first, that paper was, except for this intuition, was poorly written, had a serious mistake. It had a factor of 2 wrong in the strength of gravity, which meant if we used those formulas, we would. And 2 years later, he wrote a second paper. And in that paper, it turns out to be important for us because in that paper, he not only fixed his factor of 2 mistake, which he never admitted, he just wrote it, fixed it like he always did. And then he told us how you make gravitational waves, what makes gravitational waves. And you might recall in electromagnetism, we make electromagnetic waves in a simple way. You take a plus charge and minus charge, you oscillate like this, and that makes electromagnetic waves. And a physicist named Hertz made a receiver that could detect the waves and put it in the next room. He saw them and moved forward and backward and saw that it was wave-like. So Einstein said it won't be a dipole like that. It'll be a 4-pole thing. And that's what it's called, a quadrupole moment that gives the gravitational wave. So he saw that again by insight, not by derivation. That set the table for what you needed to do it. At the same time, in the same year, Schwarzschild, not Einstein, said there were things called black holes. So it's interesting that came the same.
So what year was that? So
1915.
It was in parallel
with.
I should probably know this, but did Einstein not have an intuition that there should be such things as black holes?
That came from Schwarzschild.
Oh, interesting.
Yeah. So Schwarzschild, who was a German theoretical physicist, he got killed in the war, I think, in the First World War, 2 years later or so. He's the one that proposed black holes, that there were black holes.
That feels like a natural conclusion of general relativity, no? Or is that not?
Well, it may seem like it, but I don't know about a natural conclusion. It's a result of curved space-time, though.
Right, but it's such a weird result that you might have to. It's a special.
Yeah, it's a special case.
Yeah.
So I don't know. Anyway, Einstein then, an interesting part of the story is that Einstein then left the problem. Most physicists, because it really wasn't derived, he just made this, didn't pick up on it, or general relativity much, because quantum mechanics became the thing in physics. And Einstein only picked up this problem again after he immigrated to the U.S. So he came to the U.S. in 1932. And I think in 1934 or 5, he was working with another physicist called Rosen, who he did several important works with. And they revisited the question. And they had a problem that most of us as students always had that study general relativity. General relativity is really hard because it's 4-dimensional instead of 3-dimensional. And if you don't set it up right, you get infinities, which don't belong there. We call them coordinate singularities as a name. But if you get these infinities, you don't get the answers you want. And he was trying to derive now general relativity from general relativity gravitational waves. Mm-hmm. And in doing it, he kept getting these infinities. And so he wrote a paper with Rosen that he submitted to our most important journal, Physical Review Letters. And that when it was submitted to Physical Review Letters, it was entitled, Do Gravitational Waves Exist? A very funny title to write 20 years after he proposed they exist. But it's because he had found these singularities, these infinities. And so the editor at that time, and part of it that I don't know, is peer review. We live and die by peer review as scientists. We send our stuff out. And I don't know when peer review actually started or what peer review Einstein ever experienced before this time. But the editor of Physical Review sent this out for review. He had a choice. He could take any article and just accept it. He could reject it, or he could send it for review.
Right. I believe the editors used to have much more power.
Yeah. And he was a young man. His name was Tate. And he ended up being editor for years. But so he sent this for review to a theoretical physicist named Robertson, who was also in this field of general relativity, who happened to be on sabbatical at that moment at Caltech. Otherwise, his institution was Princeton, where Einstein was. Mm-hmm. And he saw that the way they set up the problem, the infinities were like I may get as a student, because if you don't set it up right in general relativity, you get these infinities. And so he reviewed the article and gave an illustration that if they set it up in what are called cylindrical coordinates, these infinities went away. He's the editor of Physical Review was obviously intimidated by Einstein. He wrote this really not a letter back like I would get saying, you're screwed up in your paper. Instead, it was kind of, what do you think of the comments of our referee? Yeah. Einstein wrote back, it's a well-documented letter, wrote back a letter to Physical Review saying, I didn't send you the paper to send it to one of your so-called experts. I sent it to you to publish. I withdraw the paper.
Wow.
And he never published again in that journal. That was 1936. Instead, he rewrote it with the fixes that were made, changed the title, and published it in what was called the Franklin Review, which is the Franklin Institute in Philadelphia, which is Benjamin Franklin Institute, which doesn't have a journal now, but did at that time. So the article is published. It's the last time he ever wrote about it. It remained controversial. So it wasn't until close to 1960, 1958, where there was a conference which brought together the experts in general relativity to try to sort out whether there was it was true that there were gravitational waves or not. And there was a very nice derivation by a British theorist from the heart of the theory that gets gravitational waves. And that was number one. The second thing that happened at that meeting is Richard Feynman was there. And Feynman said, well, if there's typical Feynman, if there's gravitational waves, they need to be able to do something. Otherwise, they don't exist. So they have to be able to transfer energy. So he made a idea of a Gedanken experiment that is just a bar with a couple of rings on it. And then if a gravitational wave goes through, it distorts the bar. Mm-hmm. And that creates friction on these little rings. Yeah. And that's heat. And that's energy. So that meant...
Is that a good idea? That sounds like a good idea.
Yeah, it means that he showed that with the distortion of space-time, you could transfer energy just by this little idea. And it was shown theoretically. So at that point, it was believed theoretically then by people that gravitational waves should exist.
No, we should be able to detect them.
We should be able to detect them, except that they're very, very small.
And so what kind of, there's a bunch of questions here, but what kind of events would generate gravitational waves?
You have to have this, what I call quadrupole moment. That comes about if I have, for example, two objects that go around each other like this, like the Earth around the sun or the moon around the Earth. Or in our case, it turns out to be two black holes going around each other like this.
So how's that different than basic oscillation back and forth? Is it just more common in nature to have?
Oscillation is a dipole moment.
So it has to be in three-dimensional space, some kind of oscillation.
So you have to have something that's three-dimensional that'll give what I call a quadrupole moment. That's just built into this.
And luckily in nature you have stuff...
and luckily things exist. And it is luckily because the effect is so small that you could say, look, I could take a barbell and spin it, right? And detect the gravitational waves. But unfortunately, no matter how much I spin it, how fast I spin so I know how to make gravitational waves, but they're so weak I can't detect them. So we have to take something that's stronger than I can make. Otherwise, we would do what Hertz did for electromagnetic waves. Go in our lab, take a barbell, put it on something, spin it.
Can I ask a dumb question? So a single object that's weirdly shaped, does that generate gravitational waves? So if it's rotating,
sure, it
but
will.
It's just much weaker signal.
It's weaker. Well, we didn't know what the strongest signal would be that we would see. We targeted seeing something called neutron stars, actually, because black holes we don't know very much about. It turned out we were a little bit lucky. There was a stronger source, which was the black holes.
Well, another ridiculous question. So you say waves. What does a wave mean? Like the most ridiculous version of that question is, what does it feel like to ride a wave as you get closer to the source? Or experience it?
Well, if you experience a wave, imagine that this is what happens to you. I don't know what you mean about getting close. It comes to you. So it's like this light wave or something that comes through you. So when a light hits you, it maybe makes your eyes detect it. I flashed it. What does this do? It's like going to the amusement park And they have these mirrors. You look in this mirror and you look short and fat, and the one next to you makes you tall and thin. Okay. Imagine that you went back and forth between those two mirrors once a second. That would be a gravitational wave with a period of once a second. If you did it 60 times a second, go back and forth, and then that's all that happens. It makes you taller and shorter and fatter back and forth as it goes through you at the frequency of the gravitational wave. So the frequencies that we detect are higher than 1 a second, but that's the idea. So,
But
and the amount is small.
amount is small, but if you're closer to the source of the wave, is it the same amount?
Yeah, it doesn't dissipate.
It doesn't dissipate. Okay, so it's not that fun of an amusement ride.
Well,
park ride.
it does dissipate, but it doesn't. It's proportional to the distance.
Right, it's not.
It's not a big power.
Right, gotcha. So, but it would be a fun ride if you get a little bit closer or a lot closer. I mean, like I wonder what the. Okay, this is a ridiculous question, but I have you here. I mean, like the getting fatter and taller. I mean, that experience, for some reason, that's mind blowing to me because it brings the distortion of space-time to you. I mean, space-time is being morphed, right? Like this is a wave.
That's right.
That's so weird.
And we're in space, so
we're in space, and now it's moving. I don't know what to do with it. I mean, okay. How much do you think about the philosophical implications of general relativity? Like that we're in space-time and it can be bent by gravity. Like, is that just what it is? Are we supposed to be okay with this? Because like even Newton is a little weird, right? But that at least like makes sense. That's our physical world. You know, when an apple falls, it makes sense. But like the fact that entirety of the space-time we're in can bend.
Well,
that's really mind-blowing.
Well, let me make another analogy.
This is a therapy session for me at this point.
Yeah, right. Another analogy.
Thank you.
So imagine you have a trampoline.
Yes.
Okay. What happens if you put a marble on a trampoline? It doesn't do anything, right?
No.
Just
maybe a little bit, but not much.
Yeah. I mean, just if I drop it, it's not going to go anywhere. Now imagine I put a bowling ball at the center of the trampoline. Now I come up to the trampoline and I put a marble on. What happens?
It'll roll towards the bowling ball.
All right. So what's happened is the presence of this massive object distorted the space that the trampoline did. This is the same thing that happens to the presence of the Earth and the apple. The presence of the Earth affects the space around it, just like the bowling ball on the trampoline.
Yeah, this doesn't make me feel better. I'm referring from the perspective of an ant walking around on that trampoline. Then some guy just dropped a ball, and not only dropped the ball, right? It's not just dropping a bowling ball; it's making the ball go up and down, or doing some kind of oscillation thing, where it's like waves. And that's so fundamentally different from the experience on being on flat land and walking around and just finding delicious sweet things as ant does. And it just feels like to me from a human experience perspective, it's humbling. It's truly humbling.
It's humbling, but we see that kind of phenomenon all the time. Let me give you another example. Imagine that you walk up to a still pond.
Yes.
Okay. Now you throw a rock in it. What happens? Ripples. The rock goes in, sinks to the bottom, fine. And these little ripples go out.
Yeah.
And they travel out. Yeah. That's exactly what happens. I mean, there's a disturbance, which is the bowling ball or our black holes. And then the ripples, they go out in the water. They don't have the rock, pieces of the rock.
But see, the thing is, I guess what's not disturbing about that is it's a flat two-dimensional surface that's being disturbed. Like for a three-dimensional surface, three-dimensional space to be disturbed feels weird.
It's even worse. It's four-dimensional because it's space and time.
Time, yeah.
So that's why you need Einstein, is to make it,
make it okay?
four-dimensional. No,
Well,
to make it.
to make it four-dimensional.
Yeah, to take the same phenomenon and look at it in all of space and time. Anyway, luckily for you and I and all of us, the amount of distortion is incredibly small. So it turns out that if you think of space itself, now this is going to blow your mind too. If you think of space as being like a material, like this table, it's very stiff. You know, we have materials that are very pliable, materials that are very stiff. So space itself is very stiff. So when gravitational waves come through it, luckily for us, it doesn't distort it so much that it affects our ordinary life very much.
No, I mean, that's great. Wait, I thought there was something bad coming. No, this is great. That's
bad.
Great news. So, perhaps we evolved as life on Earth to be such that for us, this particular set of effects of gravitational waves is not that significant. Maybe that's why.
You probably used this effect today or yesterday.
To do what?
So it's pervasive. Well,
you mean gravity or the way or external? Because I only
curvature of space and time.
Curvature of space. How? I only care personally as a human, right? The gravity of Earth.
But you use it every day almost.
It's curving.
No.
What?
It's in this thing. Every time it tells you where you are.
Yeah.
How does it tell you where you are? It tells you where you are because we have 24 satellites or some number that are going around in space, and it asks how long it takes the being to go to the satellite and come back the signal to different ones, and then it triangulates and tells you where you are. And then if you go down the road, it tells you where you are. Do you know that if you did that with the satellites and you didn't use Einstein's equations?
Oh, no. You went with Newton.
You won't get the right answer. That's right. And in fact, if you take a road that's, say, 10 meters wide, I've done these numbers, and you ask how long you'd stay on the road if you didn't make the correction for general relativity, this thing you're poo-pooing, that you're using every day, you'd go off the road in about a minute. The road?
Well, actually, that might be my problem.
So you use it. So don't poo-poo it.
Well, I think I'm using an Android, so maybe, and the GPS doesn't work that well, so maybe I'm using Newton's physics. So I need to upgrade to general relativity. So gravitational waves and Einstein had. Wait, Feynman really does have a part in the story? Was that one of the first kind of experimental proposed detect gravitational waves?
Well, he did what we call a Gedanken experiment. That's a thought experiment.
Yes.
Okay, not a real experiment. But then after that, then people believe gravitational waves must exist. You can kind of calculate how big they are. They're tiny. And so people started searching. The first idea that was used was Feynman's idea, and a variant of it. Mm-hmm. And it was to take a great big, huge bar of aluminum and then put around, and it's made like a cylinder, and then put around it some very, very sensitive detectors so that if a gravitational wave happened to go through it, it would go, and you detect this extra strain that was there. And that was this method that was used until we came along. It wasn't a very good method to use.
And what was so we're talking about a pretty weak signal here.
Yeah, that's why that method didn't work.
So can you tell the story of figuring out what kind of method would be able to detect this very weak signal of gravitational waves? So
remembering what happens when you go to the amusement park, that it's going to do something like stretch this way and squash that way, squash this way and stretch this way. We do have an instrument that can detect that kind of thing. It's called an interferometer. And what it does is it just basically takes usually light, and the two directions that we're talking about, you send light down one direction and the perpendicular direction. And if nothing changes, it takes the same, and the arms are the same length. It just goes down, bounces back. And if you invert one compared to the other, they cancel. So there's nothing happens. But If it's like the amusement park and one of the arms got shorter and fatter, so it took longer to go horizontally than it did to go vertically. Then when they come back, when the light comes back, that comes back somewhat out of time. And that basically is the scheme. The only problem is that that's not done very accurately in general, and we had to do it extremely accurately.
So what's the difficulty of doing so accurately?
Okay. So the measurement that we have to do is a distortion in time. How big is it? It's a distortion that's 1 part in 10 to the 21. That's 21 zeros and a 1. Okay.
Wow. And this is like a delay in the thing coming back.
It's one of them coming back after the other one, but the difference is just 1 part in 10 to the 21. Oh. So for that reason, we make it big. Let the arms be long. Okay. So 1 part in 10 to the 21. In our case, it's kilometers long. So we have an instrument that's kilometers in one direction, kilometers in the other.
How many kilometers are we talking about? 4 kilometers.
4 kilometers in each direction. If you take then 1 part in 10 to the 21, we're talking about measuring something to 10 to the minus 18 meters.
Okay.
Now, to tell you how small that is, the proton, thing we're made of that you can't go and grab so easily, is 10 to the minus 15 meters. So this is 1/1000th the size of a proton. That's the size of the effect. Einstein himself didn't think this could be measured, ever seen. Actually, he said that. But that's because he didn't, anticipate modern lasers and techniques that we developed.